All right, let's dive into a classic coding puzzle. How do you systematically find every single possible arrangement of a set of items? It sounds simple on the surface, but it's a challenge that unlocks a really powerful and, honestly, elegant programming technique. Let's get into it.
So, let's start with a simple puzzle, just to get our heads in the game. Imagine you have three distinct items. We'll just use the numbers 1, 2, and 3. How many unique ways can you line them up? You could have 1, 2, 3, or 1, 3, 2. Maybe 2, 1, 3. Seems pretty manageable, right?
Well, there's a neat mathematical formula for this. For any n items, the answer is n factorial. All that means is you multiply n by every whole number smaller than it, all the way down to 1. So for our 3 items, that's just 3 times 2 times 1, which gives us 6. Easy enough. But what happens when n starts to get just a little bit bigger?
And this is where things get, well, kinda crazy, fast. It's a problem that's sometimes called factorial explosion. For just 10 items, you're suddenly looking at over 3.6 million different arrangements. Trying to list those by hand, forget about it. It's impossible. We are going to need a much smarter, more systematic strategy.
Okay, so let's officially lay out what we're dealing with here. Let's call it the permutation puzzle.
So here's the challenge, plain and simple. We get an input, a collection of unique things, like our list of numbers. Our goal, to generate every single possible ordering of those items. And the most important rule of the game is that our process has to be absolutely foolproof. We can't miss any, and we can't accidentally create the same one twice.
So how on earth do we build a foolproof system for this? The answer is a really beautiful and powerful technique, and it requires us to start thinking recursively. Okay, so what is recursion? It sounds complicated, but the core idea is actually pretty simple. It's all about breaking a big, tough problem down into smaller and smaller pieces that are just miniature versions of the original problem. A function that uses recursion will call itself to solve these little mini-problems until it gets to one that's so tiny it can be solved instantly.
So let's bring that back to our puzzle. How does it apply?
Well, think about it like this. To find all the permutations of 1, 2, 3, we just have to decide on the first element. Let's say we pick 1. What are we left with? Well, now we just have a smaller identical problem. Find all the permutations of 2, 3. That is the recursive mindset right there.
I know, that might still feel a little bit abstract. So you know what? Let's make it crystal clear. We're going to walk through this process step by step and see exactly how a computer would think its way to a solution.
Our journey starts at a crossroads. Right at the beginning, we have 3 possible choices for that very first spot in our arrangement. We can pick 1, we can pick 2, or we can pick 3. The algorithm we build has to explore all 3 of these paths. So for this walkthrough, let's just go down the first path and pick 1.
Okay, first move is made. We've placed 1 in our current permutation. And just by doing that, the state of our puzzle has changed. Our permutation in progress is just the number 1, and the pool of numbers we have left to choose from is now just 2, 3.
So we just keep going down this path. From the choices we have left, 2, 3, we'll just pick the next one in line, 2. We add that to our list, so now our permutation is 1, 2. And we've only got 1 number left to place.
And the last step on this path? It's a gimme. There's only 1 choice left, 3. We add it, and bam! Our permutation is 1, 2, 3. The length now matches our original input. We have found a complete, valid result. We can go ahead and save this one.
Okay, that's fantastic. We found one. But wait a minute. Our goal was to find all 6 of them, right? How does our algorithm get from finding 1, 2, 3 to finding, say, 1, 3, 2? We can't just keep adding numbers. We need some way to go back and try a different path.
And this is where the real magic happens. The secret ingredient that allows a recursive algorithm to explore every possible path without getting lost is a technique called backtracking.
So here's the big idea with backtracking. After a recursive call is finished, it literally undoes its choice. So when our path was 1, 2, it made that recursive call to place the 3. As soon as that call returns, it backtracks. The path goes back to being just 1, and suddenly the number 2 is available to be used again in a completely different path. It's just like hitting the undo button on your last decision.
This whole process can be boiled down to a simple but really powerful 3-step mantra. You ready? First, you pick an available element. Second, you recurse, calling the function again to solve the rest of the puzzle. And third, and this is the most important part, after that recursive call is totally done exploring, you unpick your choice. You undo it, so you can then pick something else.
Let's watch that mantra in action to find our next permutation. We just found 1, 2, 3, so the algorithm backtracks. It unpicks the 3. Now the path is 1, 2. There are no other choices there, so it backtracks again, unpicking the 2. This takes us all the way back to when our path was just 1. From here, it can finally explore a new branch. It picks the next available choice, which is 3, and then the last remaining number, 2. And just like that, we found our second permutation, 1, 3, 2.
Now that we have the core concept down, let's get a little more formal and talk about what this looks like in code and, how efficient this strategy really is. So this is how our pick, recurse, unpick mantra actually translates into code logic. You always have a base case. That's your exit ramp. For us, if our temporary list is full, hey, we found a solution. We save it, and we're done with that path. Otherwise, in our recursive step, we loop through all of our starting numbers. For each number, we check, have we already used it? If not, we do our 3 steps. We pick it, we recurse, and then we unpick it, so the loop can continue to the next number.
All right, the big question, how fast is it? I mean, that time complexity might look a little intimidating, but it actually makes total sense when you break it down. We have to generate n factorial permutations. That's just the nature of the problem. We can't avoid it. And for each of those final answers, we basically did n steps to build it. So the total time is roughly n factorial times n. As for space, we only need extra space proportional to n, for things like the recursion depth and for keeping track of which numbers we've already used.
So, if there's one thing to take away from all this, it's this. Recursion and backtracking are like a dynamic duo. Recursion is the strategy that breaks the big problem down into smaller pieces. But backtracking is the key mechanism that lets us undo our choices so we can explore every single possible path. They work together perfectly to solve these incredibly complex search problems. This pick, recurse, unpick pattern is ridiculously powerful. Now that you've seen how it just demolishes the permutation problem, start thinking about where else you could use it. Puzzles like solving a Sudoku, generating all the combinations of a team, or finding a path through a maze. They all use this exact same fundamental logic. The puzzle might change, but that core strategy stays the same.